We've been solving systems of linear equations, and we've been finding special systems of linear equations that don't have solutions. Now we're going to look at systems of linear inequalities. If you remember last chapter, we graphed linear inequalities before, and we found that we ended up with a line, either solid or dotted, and then an area of the graph shaded. So when we have a system of linear inequalities, we have more than one of those, and our solution is going to be where the two shaded areas overlap, if they overlap at all. So let's look at example 1, which asks us to graph the system of linear inequalities given as y is greater than negative x minus 2, y is less than or equal to 3x plus 6. Now these are already in slope-intercept form, so they should be fairly straightforward to graph. We're going to start with the first equation, and we graph it just as if it were a line, except for we're going to use a dotted line because it's less than and not less than or equal to. So we notice that if y equals negative x minus 2, our y-intercept is negative 2, and our slope is negative 1. So we have a rise of negative 1 over 1, which means we're going down 1 and over 1. Or we can go up 1 and back 1 so that we have a negative or a downhill slope. So let's graph our line, and again we want to make it dotted because it's less than and not less than or equal to. So there's our first equation. The question is, which side of the graph are we supposed to highlight? Well, since as y is greater than, we're looking for all of the y values above the line, which is this area up here. Okay, now I don't want to color it in too thickly because I've got to graph the other line too, and I want to be able to see where I'm graphing. So let's graph the second line. Y is less than or equal to 3x plus 6. So again, we graph it as if it were equals, and since it's a or equal to, we're using a solid line. We see that our y-intercept is at 6, and our slope is positive 3. So it's going up 3 for every one that it goes over, or if we go down 3, we can go back 1, so we have a nice uphill line as we go from left to right. And so we graph our equation. And since that's less than or equal to, we want all the y values below that line, which is this area here. Now, as we can see, the region that they have in common is very well defined. Let's shade it in now. It's this region here. Okay, that's the area where the two overlap. So that's our solution area. Now, we can graph more than one equation or inequality when we're graphing these. We can have a system of 3 equations or inequalities if we'd like. So our first equation is y is greater than or equal to negative 1. Now if that were y equals 1, we'd have a horizontal line at y equals 1, or negative 1, which is down here. And we're using a solid line because it's greater than or equal to. So there's our first equation. And since we want y values greater than that, we want to go above that line. It's this area up here. Okay, what I'm going to do, just to give an idea, is I'm going to draw just little tiny arrows to know that I'm going above this line. That way my graph, when I'm done, will be a little neater. I can erase the little arrows and just color in the area that's the 3 inequalities have in common. For x is greater than negative 2, I know x is equal to negative 2 is a vertical line at negative 2. But since it's greater than and not greater than or equal to, it needs to be dotted. So we get something like this on one side. Oops. There we go. And since we want greater than, that's the area to the right. That's where all the x values are greater than -2. So now let's throw in the third line. Now the third line is in standard form, so we might want to use our intercepts to graph. So we find our x-intercept by plugging in 0 for y. We get x is 4. Now I just wrote equal to because that's our intercept, not part of the inequality itself necessarily. So that's where we're going to put our x-intercept right there. Okay, and then to find the y-intercept, I plug in 0 for x. And I get y is 2. Okay, and just write equal to. Okay, so that's our y-intercept at 2. So I got those 2 points, which I can connect with a solid line because it's less than or equal to form my line. Now the question is, which side do I shade? Well, I can just check a point and see if it's a solution. An easy one to check, since it's not on line, is 0, 0. So if we plug in 0 for x and 0 for y, we get 0 is less than or equal to 4, which is true. So that means 0, 0 is a solution. So this side of the line is a solution. So now I see where my final solution is. It's that area inside that triangle. So I can color that in here. And there we go. That's our solution region. Now, sometimes you'll be given a graph and you need to find a system of inequalities that fit that graph. So in example 3 in your book, you're given a graph of a system of linear inequalities, and you need to write the equations or the inequalities that fit that region. Now, what we want to do is start by finding the equation of the lines. So if we look at the horizontal one, that will be the easier of the two. Remember that horizontal lines are a y equals situation. So we know that we're going to be starting with a y equals or greater than or equal to or less than or equal to. Now, since the area is above the line, we want y is greater than, because we want the points above that line. And since it's a solid line, we want greater than or equal to. Then we just got to determine what y value we're using. So we notice that this is 2, which means that that's 1 and that's 3. So we want y is greater than or equal to 3. All of the points in that region have a y value greater than or equal to 3. Let's look at the other line, and we'll write it in slope-intercept form. So y and an mx plus b. So we need to know our slope and our y-intercept. We see our y-intercept is 1. Our slope must be positive because it's going up. And if we look at 2 points here and here, it's going over 1 and up 2. So it has a slope of 2 over 1, or just 2. And then we need to determine what symbol we want to use. Now, these points up here are all above the line. So that means we're looking at a greater than situation. And since it's a dotted line and not a solid line, we don't want the equal to, just the greater than. So there's our inequalities that describe the shaded region. Why don't you try graphing a system of inequalities on your own. Pause the video, see how it works, and then we'll go over it together. So you have y is greater than negative x, y is greater than or equal to x minus 4, and y is less than 5. Give that a shot. Alright, so if we look at the first one has a y-intercept of 0 and a slope of negative 1. meaning it's going down 1 and over 1. And since it's greater than and not greater than or equal to, we want dotted lines. Okay, there's our first one, and since it's greater than, we're looking at areas above. For y is greater than or equal to x minus 4, we have a y-intercept at -4 and a slope of +1, so it's going up 1 and over 1 each time. Okay. And since it's greater than or equal to, we can use a solid line. And greater than tells us we're looking above the line. Then y is less than 5. That's a horizontal line. Since it's less than, we're going to use a dotted line, and we're going to put it at 5, because that's the value they give us. So we get a horizontal line that's dotted at y is 5. And since it's less than 5, that means we're going below the line. So as you can see, the area that they're all pointing to is this region right in here. There's our solution region. Let's look at a word problem. The National Collegiate Athletic Association, or the NCAA, regulates the lengths of aluminum baseball bats used by college baseball teams. The NCAA states that the length in inches of the bat minus the weight of the bat cannot exceed 3. Bats can be purchased at lengths from 26 to 34 inches. So, if we let the length be x and the width, or the weight, be y, they told us that the length minus the width, or the length, I'm going to keep saying that, the length minus the weight cannot exceed, that means it has to be less than or equal to 3. Then they tell us that the bats can be purchased at length from 26 to 34 inches. That means the length is greater than or equal to 26, but less than or equal to 34. Now, as for the y, we know it has to be greater than or equal to 0 because you can't have a bat that has a negative weight. So we have our system of inequalities. Now we need to graph it. So since we don't need negative values, we can use the upper right hand quadrant for our graph. Our first equation was x minus y is less than or equal to -3. So let's rewrite that inequality and solve for y. So we subtract x from both sides, which gives us negative y is less than or equal to negative x plus 3. Then if we multiply by -1, it becomes positive y, and remember we switch the direction of the sign to be x minus 3. So that has a y-intercept of -3 and a slope of 1. So I'm just going to give a quick sketch of this. Got a y-intercept right about there and a slope of 1. Oops, gotta use a solid line because it's greater than or equal to. Then we have x has to be between 26 and 34. Which puts our vertical limits, our vertical lines, around here. 26 and 34. And y is greater than or equal to 0. So since our x values are between those two vertical lines, that's this area here, and since we had y is greater than or equal to x minus 3, that means we want to be above that diagonal line, which puts our final limit right here. Then it asks if we can sell a bat that weighs 31 inches long and weighs 25 ounces. Well, if we look, 31 inches long is right about here. 25 ounces is right here. That's not part of our solution set. So we can't sell a bat with those restrictions because it doesn't fit in our solution region. Alright, if you have any questions, feel free to ask. If not, you can get started on your homework.